Hello students, in this video I will be talking about the inverse of an exponential function, which is also known as a logarithm function. So we've talked a lot about graphs of exponential functions. I've dedicated 2 videos on graphing exponential functions. And in the last video, it was discussed that the exponential function, when graphed, will pass the horizontal and vertical line tests regardless of what kind of transformations have taken place. All exponential functions will have an inverse function. So now let's actually talk about it. So let's talk about a a general kind of exponential function. Generally, exponential functions will have this kind of shape. I don't care for what the y-intercept is for the moment, okay? But generally, it will have this kind of shape. If I wanted to find the inverse function, what I have to do is I need to take this and reflect it over the line y equals x. And if I perform the reflection, this is the shape of a graph that I'll end up with. That right there, ladies and gentlemen, is the inverse function that we've been looking for. This is this is otherwise known as the logarithm function. So the question still lingers though, how do we isolate x, say in the equation y equals to 2 to the x, right? Remember, our goal from like 3 videos ago was to try and solve 5 is equal to 2 to the x. So if we can isolate x in this equation here, we have our inverse function, and then we can be able to solve that, right? Sorry to break it to you, but we really cannot isolate x. Not with the traditional means, that is. We cannot isolate x by performing reverse PEMDAS. Okay? So there's nothing that we can divide, multiply, add, subtract, or raise, okay, either side by any particular power to try and isolate x. Because of this, again, I've said that already. Because of this, okay, mathematicians invented a machine, and I place machine in quotation marks because this is all very theoretical and philosophical, right? All of math is just one big philosophical project, if you really think about it. So mathematicians invented this machine, okay, which represents the inverse of the exponential function. So this is a common thing that math and science people do. If they don't know something and they understand what they don't know is the thing that they're trying to like reach, right? They'll call that unknown something so that they can then work with it. This is actually part of like problem solving and scientific method, right? It's all a part of that. If you don't know something, name it, right? And then work with it, make observations, and then conduct experiments. That's all a part of that same process. So this machine, okay, mathematicians are calling logarithms, okay, such that this machine is going to do this. If y is equal to 2 to the x, then, okay, in order for us to reverse the input and output, they're going to call log of base 2 of y is equal to x. So going back to our original problem of 5 is equal to 2 to the x, how do we solve for x? Well, that's simply log base 2 of 5. And that is going to be, this is the answer that we've been looking for. I know this is not the best answer that you've been looking for, okay, but that is the exact answer. Let's talk a little bit more about what this is, what's the significance of this, and how do we like utilize this and like really familiarize ourselves with this, okay? So anyway, the inverse function, okay, is the logarithm. So let's say if we have y is equal to 10 to the x, then log base 10 of y is equal to x. Or simply, if I have a is equal to b to the c, then log base of b of a will equal to c. So again, what mathematicians did to find a logarithm of a number with a particular base before the age of computers was to create tables of exponential values. Then by applying properties of inverse, they've created the logarithm table. I know it's very archaic and almost borderline like troublesome, right? To think about. There's no like quick way of doing things, and you know, a lot of things in the world, right? At first may seem like it's an impossible thing, but through time and through a lot of investigation, okay, we then discover different ways of solving things. You know, take for example like Google. They were one of the first ones to like download everything and collect data from everybody, right? At first people thought that was nuts. Well, that then became like a common practice, okay, amongst like Silicon Valley. Well, same thing can be said about this. If we don't know how to solve for these different values, well, why not start from scratch, right? Why not just create an exponential table? So that's what mathematicians did, okay? And they've created all these different tables, okay? And how do we use this table? This is an example, a snipping, okay, of an exponential table. How do we use this? This is saying 10 to the 0 is equal to 1. 10 to the 0.1 is equal to 1.023. 10 to the 0.02 is equal to 1.047. 10.021 is equal to 1.05, and so on, okay? This is how you read the table. I'm not showing you the details of how to read the table, and actually there's a lot of steps and a lot of things that you need to be aware of in order to use an exponential table as well as a logarithmic table. I'm not going to get into the details of that, but I'm just telling you a little bit about the history here. Okay, so they've created these tables where people have found the exponential values. Okay, and so by knowing the exponential values moving forward, they can then generate numbers going backward, which is the inverse, right? So they have these exponential tables. They also have these logarithmic tables. So how do we read these logarithm tables? Well, these logarithm tables are saying this: 10 to the x is equal to 10.1, right? 10 to the x is equal to, let's say, 10.1. Where am I getting 10.1 from? Well, this is the same thing as the answer to that is 1.043, right? So again, I'm taking this. This is the solution. 10 to the 10.1. I'm sorry. 10 to the some power is equal to 10.1. That's equal to 1.043. 10 to the something is equal to 11.1. So this guy right here, right? 11.1 is equal to 1.0453. 10 to the x is equal to 12. This guy down over here, right? That's saying x is equal to log base 10 of 12.1, which is equal to 1.0792, and so on. So these tables here, okay, provide us with a way to figure out logarithms. Okay? These logarithm tables and these exponential tables from before, right? These are all a part of our human evolution and our human history. These are relics of the past, and you know what? In poorer countries, okay, the abacus, okay, and slide rule and the log tables and exponential tables, okay, all of these things are still used. Okay, it's just we're in the United States, we're a wealthier country, okay, that we're fortunate enough where everyone is able to afford these computers, okay, where we can then generate these very same results without having to look these things up. Think of the age before before computers or before smartphones, everyone had to use a dictionary, right? When was the last time you ever looked up a word out of a book? Anyway, so now your calculator, okay, is programmed by default to compute numbers of base 10 and base e. Okay, the number e will be discussed at a later point, so I'm not going to talk much about that, but your calculator can only compute things out of base 10. So please understand, log base 10 of x is equal to log of x. By default, okay, if there's no base written there, then by default it is always base 10. Your calculator can only perform computations of base 10 or base e. Your calculator will not say log base e, but instead use this notation, ln. Okay? So if you see ln, that means it's base e. ln actually stands for the natural log. I know it's backwards. Okay, so getting back to how can we actually solve this problem, 5 is equal to 2 to the x? We don't have the right tools, you may be wondering, all right, or the right logarithm function for that matter, okay, of base 2. If our calculator only operates in base 10, but this problem involves base 2, how can we then solve this problem, you may be wondering? Well, we need to investigate more time into the properties and graphs of logarithms before we can answer this question. I know it's a very long-winded answer, okay, to this problem that I posed like 3 lessons ago. But we're still investigating. We're still getting there. I promise, okay? All right. So, some identities, okay, of logarithms that you should be aware of that, perhaps maybe you can conclude on your own as well. And that is, okay, the conversion going from exponential form to logarithmic form, okay? If I have a is equal to b to the power of c, then we can re-express this as log base b of a is equal to c. Log base a of a is equal to 1. Log base a of a will always equal to 1. Anytime you're taking a log of a number where it's the same as the base, right, it will always equal to 1, because in other words, this is the same thing as saying a to the first is equal to a. Or in other words, log of 10 will equal to 1, because this is the same thing as saying 10 to the first is equal to, you guessed it, 10. So log of 10 is equal to 1. Log base a of 1 is equal to 0. That's because a to the 0th is equal to 1. Log of 1 is equal to 0 because 10 to the 0 is equal to 1. Log of base anything of 1 is equal to 0. Log base a of 0, on the other hand, is undefined because this is not possible. A raised by a number can never be 0. Think about this. If you have a raised to some number, can it ever equal to 0? This goes back to the understanding of, again, graphs of an exponential function, right? An exponential function can never dip below 0. Remember that, right? So because of this, the log of 0 is undefined. It will never happen. And as a matter of fact, log of a negative number, okay, cannot happen, because can you think of a number where a raised to something, okay, equals to something that's less than 0? Let's say something like -5. This is, again, not possible. In the next video, I will be applying these identities in exercises.